Okay, we're going to look at kinematics in one dimension. And kinematics basically is the study of motion. We use such variables as distance, displacement, speed and velocity, acceleration, and time. So let's take first look at displacement or distance. So if we have a car in two locations, initial location here on the left and a final location, we'll put them on a number line and we can put their displacement or their position. This car is at -6 on the number line. This car is at +4. Okay, so what we want to find is something called the delta x. Okay, little Greek letter in front of the x. Okay, and so we have x2 minus x1, that is the final minus the initial displacement. Plug in the numbers and we get 10. So the distance from this point, x1 to x2, is 10. And also the direction is to the right. Now you could have the opposite. If this was x2 here and this was x1, you would have -10. The negative would just mean the direction. The negative would be towards the left. So basically, in kinematics, we first start off with one direction, and we have three actually variables that we use. And you see the little arrow on top of V, which stands for velocity. X stands for distance or displacement. A stands for acceleration. So when dealing in one dimension, we'll use either negative or plus signs to denote which direction. So let's look at an example. We're showing two vectors. One is velocity and one is acceleration. Now you notice that in this case, velocity is going towards the right and acceleration is going to the right. So this object has a velocity but also has an acceleration. The second example is deceleration. Now we have movement, we have velocity, which is to the right, but we have acceleration, which is to the left. And this is causing an object which is moving towards the right to slow down, decelerate. And we have the same thing in example 3 here, but in the opposite direction. We have the motion of velocity going into the negative direction, okay, and then we have the acceleration going the opposite direction, and this is causing deceleration. So we have to be careful on the plus and negative signs. This is a negative sign. It simply means that the velocity is going in the negative direction. Sometimes you'd be given a problem. It'll tell you negative acceleration, and you can't assume that it just means deceleration. So velocity and constant velocity. V is equal to delta x over delta t, the change in position over the change in time. And we usually will write it like this right here, where x, a nod, is the initial position, and x without the subscript is the final position. We just dropped a delta on t, just makes it a lot easier doing it this way. Okay, so in a constant velocity, we have x versus t, and this is basically, this line here is velocity. Okay, so if we take the slope, we have delta x over delta t, rise over run, and that's going to be equal to velocity. But this velocity is constant, meaning there is no acceleration. So let's look at an example. And we just have to solve for delta x, plug in the numbers, and how far has he walked? 1.5 miles. Now let's talk about acceleration. Velocity versus time graph. If we plot the motion as velocity versus time, then we have a slope that will be equal to the acceleration. So let's look at one other concept before we move on to more acceleration. Let's look at the average velocity. The average velocity is where you have two different velocities. You may have an initial velocity and a final velocity. You add those up, divide by 2, that gives you an average velocity. Okay. So if you want to calculate the average velocity of a car, let's say starting at 0 meters per second, reaching a final velocity at 27 meters per second in a time of 5 seconds, how far does the car travel in time? And so we just plug in the values and we find our average velocity. Now, where average velocity will come in handy is when you have a problem where there is an acceleration in it, and we'll get into that in a second here. This is how far does a car travel in that time. Okay, so you have time that you need to find. Okay, so we can look at this equation right here. Delta of x equals the average velocity times t. This is going to give us the distance it travels in that certain time, which is 5 seconds. So how far does a car travel in that time, 5 seconds? 67.5. Because there's a change velocity, a time of 5 seconds, there is a constant acceleration. So calculate the acceleration. We're going to use this equation where we have the change of velocity divided by the time, plug in the values, and we get 5.4 meters per second squared. Where acceleration, the units of acceleration are always meters per second squared. Let's look at the 3 acceleration equations. The first one has, actually it's second degree. It has 2 terms. The second one does not have time in it, so you don't need time where you have a problem where you don't know the time and you're not looking for it. You could use this equation. And the second is the most simplest acceleration equation, which is used a lot. These 3 equations you would probably be using quite a bit in the first course of physics, college physics. Okay, so let's look at some problems using these formulas. In the book, you will see how these formulas are derived, okay, from graphs and such. I'm not going to go through that. You can look in the book. So let's look at a problem. We have a race car travels from an initial velocity of 10 meters per second, accelerates at 2.5 meters per second squared, and travels a distance of 100 meters. So what are we given? We're given the initial velocity. We're given an acceleration. It's not negative, so it's increasing in speed, and we also have a distance that the vehicle travels before reaching a final velocity. So A, it wants us to find the time it takes to reach the final velocity. So the question is, which one of these acceleration equations do we want to use? It also wants us to find the final velocity, and it wants us to find the average velocity. So I think this equation would be the best because we know the initial velocity, v sub naught. We know the acceleration. We also know the displacement, which is 100 meters. The only thing we don't know in this equation is t. So we can solve for t. In this case, we're going to need to use the quadratic equation, okay? And I'm going to set up the quadratic equation first in this format, which you should be familiar with. And then we have the quadratic equation itself. We plug in the values, and then we solve the problem, and we get 5.79 seconds. Now you're going to get two different answers when you do a quadratic. One's going to be negative. We don't have negative time, so you won't use that one. So let's find what the final velocity is. And this is the equation right here we're going to use. And we're going to solve for the final velocity, which already is in this format already, and it's 24.47 meters per second. How about the average velocity? Well, we use the average velocity equation right here, plug in the values, and we get 17.24 meters per second. Let's look at another application of acceleration equations in one dimension. Okay, this is using v equals v sub naught plus at, or simply acceleration is equal to the change of velocity or the change of time. So let's look at a car can change velocity while accelerating from 30 miles an hour to 60 miles an hour in a certain time frame of 3.4 seconds. Find the constant acceleration. This is a simple problem where all known variables are in the equation except for the acceleration. We then solve for acceleration. But first, we must convert this variable into the MKS system. The MKS system is meters, kilograms, and seconds. Okay, we don't want to work in miles per hour in this particular problems. Sometimes you would be able to if they were asking you to find the answer in, say, miles per hour. In this case, we want to change it because we're working with an acceleration, and it would be pretty complicated to work in miles per hour with the converting accelerations. Okay, so the first thing we do is we convert this 30 miles an hour to 13.4 meters per second, and we do the same thing with the 60, and we get our velocities in meters per second. Then we use the acceleration equation. This equation up here is just this. We just solve for a. Okay, plug in the values, and we get our acceleration of 3.94 meters per second squared. Okay, let's look at another problem. Find the time it takes for an airplane to accelerate from 125 meters per second to a distance of 1 kilometer at an acceleration of 3.5 meters per second squared. So they're giving us the acceleration. So we're not given the final velocity, which correlates to the speed after it has gone 1,000 meters. The solution, this problem will require us to use, again, the quadratic equation. So we have the quadratic equation, and you should always set this up this way. Take your variables. That way you won't forget when you plug them into the quadratic equation. Okay. So here we have our quadratic equation coming up. I substitute the values in here, plugged them into the quadratic equation, and found the time it took, 7.26 seconds. So it takes 7.26 seconds for the aircraft to reach the final velocity. How can we find this velocity? We're not given it, we need to find it. So since we know the time, the easiest equation to use is this one right here. And this is going to be solving for the final velocity. Plug in what we know, and we get a final velocity of 150 meters per second. Let's look at another problem. An airplane crash lands on its belly at 80 meters per second. It then continues on for 30 seconds later and at 60 meters per second. How far did it travel before hitting the pole? So it's telling us a couple things. It's telling it lands at 80 meters per second, that's the initial velocity, and then hits a pole at 30 seconds later at a certain velocity, 60 meters per second. So the biggest thing, the problem that students have a lot of times is interpreting what the variables are and how to put them in the equation. So we know that we have what? We have the initial velocity, a final velocity, and we also have a time. How far did it travel before hitting the pole? So we need to find distance or displacement, okay? Then it wants us to find what the acceleration is. In this case, it's going to be deceleration. So solve for part A. First method, use the average velocity equation. So that's where I'm going to show you where the average velocity equation can come in pretty handy. Okay, so we have here we have the average velocity equation, and I have plugged in the two velocities, okay, and got 70 meters per second. Okay, then we take this equation right here. Now you see the v, the average velocity in here, is equal to the 70. And so very simply we can find the displacement by taking the 70.0 meters per second, the average velocity, times the 30 seconds. And we get the distance that plane travels in 30 seconds is 2,100 meters. Okay. So find the acceleration, in this case, deceleration. So we know that it's decelerating, okay? How do we know that? Well, we have a final velocity of 60, initial of 80. That's going to give us a negative number, and the time is 30 seconds, and so we get a negative 0.667 meters per second squared. So if I wanted to check this core acceleration equation, I can use this equation too. This is a different equation. And if we solve for delta x right here, we should get the same thing. We should get something around 2,100 displacement. Okay, so I'm going to solve for x, and this is this part right here. I'm going to plug in the values, and I do get the displacement of 2,100. So that was done two different ways. One, by using average velocity. Two, by using this equation right here, one of the acceleration equations. Okay, let's look at another problem. A jet fighter landing gear leaves the ground at 55 meters per second on takeoff, and for 5 seconds travels the distance horizontally in the air for 338 meters before raising its landing gear. So let's look at the problem, what we were given. Well, we're given that it's talking about a landing gear that leaves the ground at 55, when the plane is going 55 meters per second on takeoff, and the plane travels 5 seconds, a distance which is horizontal, for 338 meters before raising its landing gear. So during that period of time, they want to know what is the acceleration in this period. They also want to know what is the jet's velocity when the gear does raise, and see what's the jet's average velocity during the landing gear, raising and taking off. Okay, so A, what is the acceleration in this period? So we're going to have to use this equation right here, because look, let's see what we got. We have 55 meters per second. That is the initial velocity. We have the time to give us the time, 5 seconds, and we also have the displacement, 338. So this equation is going to work just fine. Now, is there another equation we could use? Yes, there is. You probably could use the average velocity equation, which I did in the last problem. Well, let's do it this way, using this equation. So we plug everything in, and we take this equation right here, and we solve for acceleration. And that's what we're doing right here. Plug in the values, and we get the acceleration, 5.0 meters per second squared. What is the jet's velocity when the gear raises? Okay, so we need to find a final velocity. Okay, so this would be the best equation to use, and it's already solving for the final velocity, so we just need to plug in the values. Okay, and we get 80 meters per second. What is the jet's average velocity? Well, since we know the initial and we know the final velocities, we can add them up, divided by 2, and we get the average velocity. Okay, let's look at something now besides an airplane. Let's look at a truck that's traveling at 30 meters per second. Notice as the car is stopped in the lane, the truck is moving in. The driver in the truck applies his brakes approximately 133 meters from the car that he's about to hit. The driver slams on his brakes and decelerates at 3.00 meters per second squared. Now this problem, first of all, again, look at what you have. What is the problem giving you? Well, it's giving right here, a truck is traveling at 30 meters per second. Is that constant velocity? No, it's not, because he slammed on his brakes. So we know there's deceleration. So this right here, this has got to be initial velocity. And as we read on, we can see that we have a displacement of 133 meters. This is our delta x in our problem. The driver slams on his brakes and decelerates. It tells us that he decelerates at 3 meters per second. Even though it does not have a negative sign in here, it doesn't mean that you won't have to put one in. Since we are assuming the truck is going, let's say, in the right direction, positive side, this 3 is actually a negative 3. And we know that because of it decelerates. So it wants us to find the velocity of the truck when it hits the car. So we'll use this equation. Why? Well, we don't have time. We're not using time right now. And so this is going to be the best to find actually the velocity right here. So we're going to solve for this b. So when we do, we get this expression right here. And then we just plug in the values that we know. And we get an answer of 10 meters per second. So the truck is traveling at 30 meters per second. Notice the car is stopping. He puts his brakes on 133 meters from the car, and he doesn't hit the car. And by the time he's at the car, he's going a velocity of 10 meters per second. The final velocity is still going to be positive, but the acceleration will be negative. What is the amount of time that passes until the truck driver applies his brakes and collides with the car? Okay, well, we can use this as an acceleration equation because there is an acceleration. Okay, and notice too right here, we're going to plug in the values. We have a final velocity, we have initial velocity, and we have our deceleration, negative 3.00. Okay, and this is going to give us our time, which is 6.67 seconds. Let's look at another problem of a car. Car from rest can travel 120 meters in 6 seconds. So here is telling us very little. It's telling us this car could travel a displacement of 120 meters in 6 seconds. However, there's a clue here, rest. That gives us our initial velocity of 0. So now we need to find its acceleration. Then its final velocity at 6 seconds. And find its average velocity again. Calculate displacement with it. Okay, so find its acceleration. We know that v sub naught is going to be equal to 0. And so we're going to use this equation right here. Now, because it does equal to 0, this term right here, it cancels out, making the problem much more easier. Okay, and so now we just solve for A. And when we solve for A, we get this equation. Okay, then we just plug in what we know. We only know 2 variables, 120 meters in 6 seconds. Plug them in, and here we get the acceleration that the car undergoes, 120 meters in 6 seconds. Its final velocity at 6 seconds. How do we find that? Well, we can use again this equation. Plug in what we know, and we get our answer, 40 meters per second. Find the average velocity, again using the average velocity equation, 20 meters per second. Okay, now we're going to go to the second part of kinematics in one dimension. And this is going to be a prelude when we get to chapter 3, when we start going into projectile motion. So free fall kinematics. Objects drop from a certain height above ground are subject to the effects of gravitational force. This gravity effects causes objects to accelerate toward the ground in free fall. Okay, and this acceleration of gravity, which is part of the force of gravity, is denoted by a constant, a little letter called g. So we have our equation. If we have a ball up here and we have it at a certain height, it's going to fall down, right? Okay, and it's going to fall down, and we're going to use this equation right here. This equation looks very familiar to one of the acceleration equations, except for one of the terms missing. That term would be the v nod t. We have initial velocity of 0, so we don't need that term. So we have this term right here. So the height, if you know the height, you can find the time. If you know the time, you can find the height. And the g is equal to negative 9.8 meters per second squared. Always a negative. So g is a constant, is the acceleration of gravity, where the minus sign only denotes direction. In this case, we're working in one dimension. Up is plus, down is negative. Okay, so let's look at another situation where we throw something, an object, a ball, what have you, up to a certain height with a certain initial velocity going upward. Okay, so this is one of the equations that you'll see a lot in this course, especially in projectile motion. Okay, it already has a negative in it because g is negative. Now we could put a plus sign here, but I like to just keep the negative there so I know that g is always going to be negative anyways. Okay. So for example, calculates the time. This will calculate the time it takes for the ball to reach its maximum height. So just think about this. If you have some initial velocity, it's going to go up a certain height. It's going to be fighting gravity until it gets to a certain point up here where its velocity in the vertical it becomes 0. And then it's going to be coming back towards the ground. It's actually going to hit the ground with the same initial velocity it was thrown at. Now, considering this is in a vacuum without air. So let's move on. Now we're going to take this equation right here and we're going to put it into a format that we can use in a quadratic equation. Okay, the negative 4.9 is negative 9.8 divided by 2. So in this equation, we need to put this into some type of quadratic equation. Since delta y, which is a displacement in the vertical, will equal 0. Why does it equal 0? Because start off with what is y initial? Y initial is 0 right here. It's 0. It comes back up. It comes back down. Y final is 0. 0 from 0 is 0. So what happens, this term is gone. And so all we have really is this to solve in this particular problem. So these problems where the ball or rocket, whatever projectile goes up, comes back down to the same height it started, basically we can get rid of the third term and we don't have to use the quadratic equation. Okay, so here we just solve now for the time and we get 2.04 seconds. So we use the quadratic equation in this, and I'm just showing this again, how we did it, went through it. All right. So what about the height? Okay, well, when the ball reaches its maximum height, of course, its velocity in the vertical, in the plus or the positive direction, which is going up, is eventually, because of the gravitation working on the ball, it's going to slow it down to where it reaches zero. When it reaches zero, then gravity is going to take over completely and it's going to fall back to Earth, okay? So when v equals 0, the ball will turn downward, lose energy, and fall. And so we can take this acceleration equation, which we've used in the past for some of the horizontal problems, 2g times delta x. So this is our acceleration, 2g, and this is delta y max is going to be what our height is, okay? So we just have to solve for that. And we do plug in the values, and we find we get 5.10 meters. That is the maximum height the ball goes at the initial velocity of 10 meters per second. What about we have a building, okay, and we have, let's say, a ball that a boy throws off the building upward. It's going to go up as high as it can go before it reaches its vertical velocity of 0, and then it's going to come down. We want to find the complete time the ball is in the air from where he threw it all the way to its highest point down to the ground. And this is on a building, or say it could be a ledge, it could be anything, mountain. It's 100 meters high. So the first thing we need to do is that we need to take the point of where the ball is being launched, and that is going to be our 0 point for the y-axis, okay? And so if we look at displacement, it starts off at 0 and it ends up at negative 100. So our delta y is negative 100. Okay, so I'm taking that equation, putting it into this equation, setting up for a quadratic. Notice that we have the negative sign, negative 4.9. That's 1/2 of the negative 9.8. And then we set up this way. Now, because we have a negative 100 right here, okay, when we do put it on the other side of the equal sign, we get a positive. So we have to solve now for this equation, quadratic equation. So when I'm not going to do it here, but when I plug it into the quadratic equation, I get the time of 5.65 seconds. Okay, and then the maximum height is 5.10 plus the height of the building, and that's 105.1 meters. So from here to here is the 1.5. All right, so that is how you do a problem like this off a building. Okay, let's do a problem now that's a little bit different. A rocket is shot up with an initial velocity of 100 meters per second. Find the maximum height. Find the time it takes to return to the ground. And the same problem, but off now a 100-meter building. Okay, so let's start. Okay, first of all, we're going to find the maximum height it's going to go. And so we solve for delta y max using this equation. Okay, and we get 510 meters. So that is the maximum height. That's delta y. Now to find the time it takes, well, we simply use this equation right here, this acceleration equation, and this is going to be 0 right here. So we have this equation down here, and we just solve for t, and we get t is equal to 20.4 seconds. Okay. Let's look at the last part, which is off a 100-meter building. Okay. Same thing. We're going to find the time. We're going to set up a quadratic equation, plug in the values, solve for t using the quadratic equation. Okay, and we get 21.36 seconds. Now that is from the time where the ball is launched right here, going all the way up and going all the way down. And the maximum height is just 510 meters plus 100 meters, the height of the building, which gives us an answer of 610 meters.